Hi everyone, welcome back to PRAKASAM tutorials. In this video, I am going to discuss about Poisson distribution concept. So what is a Poisson distribution? The Poisson distribution can be determined as limiting approximation to the binomial distribution under the conditions that the number of the trials small n is infinitely large and the probability of the success small p is infinitesimally small. So infinitesimally small means that is p tends to 0. But the product n into p is equal lambda is a constant. So this is the Poisson distribution definition. So in previous class we have discussed about binomial distribution concept. The Poisson distribution can be determined as the limiting case of the binomial distribution under the condition. And what is that condition? The number of independent trials small n is infinitely large, n tends to infinity, and the probability of the success p tends to 0, but the product n into p is equal lambda is a constant value. So using this condition, we can determine Poisson distribution expression from the binomial distribution. The probability of for each trial is given by P is equal lambda by n, where P is the probability of the success. But n into the product n into P is equal to lambda. Here small n is the number of independent trials and small p is the probability of the success. And from this equation, the probability of the success P is equal to lambda by n. So which is the probability of the success for each trial. But we know that P plus Q is equal to 1. P is the probability of the success, Q is the probability of the failure is equal to 1. P plus Q is equal to 1. From that expression, Q is equal to 1 minus P. But here, the probability of the success P is equal to lambda by n, and substitute this value into Q is equal to 1 minus P expression, we get the probability of the failure for each trial is given by Q is equal 1 minus lambda by n. Now let us derive the probability distribution for Poisson distribution function by applying the limiting cases. So now consider the binomial random variable capital X with probability density function is probability of m is equal NCM into p power m into q power n minus m for m is equal to 0, 1, 2, 3 and so on n. So this binomial random variable of the probability density function is already explained in my previous video. So please refer that video. So now here consider the binomial random variable with the probability density expression. In that expression, substitute the probability of the success. And what is the probability of the success? Here P is equal to lambda by n. And what is the probability of the failure here? Q is equal to 1 minus lambda by n. And substitute P and Q values into here. We get probability of x is equal to m is equal NCM into P power m. Now your P is lambda by n whole to the power of m into Q is 1 minus lambda by n whole to the power of n minus m. So the expansion of the NCM is n factorial by m factorial into n minus m factorial into lambda by n whole to the power of m into, so this factor is written as 1 minus lambda by n whole to the power of n divided by 1 minus lambda by n whole to the power of m. So now here on RHS side, the expansion of the n factorial is n into n minus 1. Applying the n factorial expansion. In the denominator is also applying n minus m factorial expansion. So we get probability of x is equal to m or probability of m is equal. The expansion of the n factorial is n into n minus 1 into n minus 2 into n minus 3 and so on n minus of m minus 1. So n minus of m minus 1 multiplying within the bracket minus we have n minus m plus 1 into next term is n minus m into n minus of m plus 1. Multiplying minus within the bracket term, we have n minus m minus 1 and so on 2 into 1. So this is the expansion of the n factorial divided by, so m factorial is written as it is same into n minus m factorial expansion is n minus m into n minus m minus 1, n minus m minus 2 and so on 2 into 1 into lambda by n whole to the power of m into 1 minus lambda by n whole to the power of n divided by 1 minus lambda by n whole to the power of m. So now we are on RHS side, numerator and denominator n minus m into and so on 3 to 1 is cancelled. So the remaining RHS term is probability of x is equal to m is n into n minus 1 into n minus 2 and so on n minus m plus 1 divided by m factorial into lambda by n whole to the power of n whole to the power of m into 1 minus lambda by n whole to the power of n divided by 1 minus lambda by n whole to the power of m. So RHS side of this term is also written as lambda power m divided by m factorial into n minus 1 and so on n minus m plus 1 divided by n power m. So this lambda by n whole to the power of m is written as lambda power m into n power m. So that is also written as this one into 1 minus lambda by n whole to the power of n divided by 1 minus lambda by n whole to the power of m. So now here there are small m number of terms available in the numerator of the term within the bracket. So dividing each term by n power m. So now we are the within the bracket term n power m. So that n power m is n into n into n into and so on n. So n into n into n into and so on n is n power m. So that n power m is written as n into n into n into and so on n. So dividing that within the bracket term, dividing each term by n. So this is 1. So therefore probability of x is equal to m is equal lambda power m by m factorial into 1 minus lambda by n whole to the power of n divided by 1 minus lambda by n whole to the power of m into. So this within the bracket term, dividing each term by n, we get n by n is 1, n minus 1 by n is 1 minus 1 by n into n minus 2 divided by n is 1 minus 2 by n and so on n minus m n minus of m minus 1 n minus of m minus 1 divided by n is 1 minus m minus 1 divided by n. So but we know that the standard expression of the binomial distribution function, and that standard expressions are limit m tends to infinity 1 plus 1 by m whole to the power of m is e, and limit n tends to infinity 1 minus lambda by n whole to the power of n is equal e power minus lambda, and limit n tends to infinity 1 minus lambda by n whole to the power of m is equal to 1. So these are the standard conditions. So using this condition, in the above expression, taking the limit n tends to infinity on both sides. In the above expression means this expression on both sides taking limit n tends to infinity, we get limit n tends to infinity into LHS term is equal limit n tends to infinity into RHS term. So using these conditions, the RHS term of this equation is, so when you are applying the limit value, now what is the limit value? Limit n tends to infinity. Limit n tends to infinity 1 minus lambda by n whole to the power of n is e power minus lambda. Limit n tends to infinity 1 minus lambda by n whole to the power of m is 1. Okay. And here within the bracket term, applying the limit value 1 by infinity is 0, 2 by infinity 0, 3 by infinity 0, m minus 1 by infinity 0. So therefore, the RHS term of this equation is using these conditions. We get limit n tends to infinity, probability of m is limit n tends to infinity, probability of x is equal to m, or simply probability of m is lambda power m by m factorial into e power minus lambda. For m is equal 0, 1, 2, 3 and so on n. So this equation is called as Poisson distribution expression. So this is the derivation of the Poisson distribution. The Poisson distribution is mostly applied to counting type problems. That counting type problems describes the number of telephone calls made during a period of the time and the number of defective elements in a given sample and the number of electrons emitted from a cathode in a given time interval. So these are the importance of the Poisson distribution. The Poisson distribution is mostly applied to counting type problems. So that counting type problems are described as this one, and that are the number of defective elements in a given sample, the number of electrons emitted from a cathode in a given time interval, and next one is the number of items waiting in a queue.